minutes for a number and stick to it, assuming you allocate 27 minutes, you'll be able to finish the 5 numbers in about 135 minutes, giving you a balance of some good number of minutes, that you can actually allocate to the parts that seem to be very hard as we are going through that. The other advantage is that if you are in an examination, a room, don't struggle to pause while you interface a slightly hard question for you. That is where time is lost. When you meet a slightly hard question, please skip either the space and proceed with other things instead of sitting and starting to scratch your head, starting to look at the ceiling like they normally say, and nothing is coming through. And again, regular revision will help you to ensure that the answers are always near the surface of the brain. The brain operates I usually say it's like a computer. When you read a question, it sends a signal to the brain, and the brain will check whether you actually know the answers to this question, and it will depend on how often you have actually been revising. I will wind up. There is a lot to share by saying that if you want to be the best, my dear candidates and all students following there, if you want to be the best, you must work more than the rest. There is no pain without gain. I think that is one of the school's motto somewhere. And the other school motto is Gachali Mabaga. It's just the beginning, so little done, so much to do. The other is that you should never give up. So if you study the different mottos of different schools, you will actually be able to note that they are all motivational. They are encouraging students to work hard. I told you that successful students don't do different exams. They simply do their exams different from the other students. We can start our lesson from where we stopped. There is a question you are seeing there. We are winding up on capacitors today. And of course, there is a variety of questions. But I have ensured that we adequately attempt the most key questions. I've touched everything that is very key. And therefore, anyone who actually looked at this topic for the first time should find questions familiar. I want to say that this particular type of question is very common. Very common. Even in last year's paper, it was there. Now, we are going to interpret this number here. And they are saying a capacitor of capacitance 10. If this is our capacitor with 10 microfarad, is charged to a PD of 20 volts. So we will connect it to a supply of 20 volts. I'll call this part A. Another separate capacitor of capacitance 20 is charged to a PD of 12 volts. In our last lesson last weekend, you will recall that we did a number similar to this one. This one is charged to 12 volts, and its capacitance is 20. That illustrates the sketch of the two statements, and they are telling us to find the total energy stored by the two capacitors. Now, to go straight to the answer, we'll recall. I will use recall. You are not supposed to use recall in an exam. For you, you just simply start. But we are recalling because we already looked at this. We saw energy, and I will pick only the formula that is direct for this number. We saw that energy is given by a half CV squared. So the total energy, if I call this C1 and this C2, and I will call this V1 in my formula and V2, I can say the E total, or for total energy, is a half C1 V1 squared plus a half C2 V2 squared. I will now substitute, given that we know these values, and I will have a half times 10 times 10 to the negative 6 times 20 squared plus a half times 20 times 10 to the negative 6 times 12 squared. And when you compute, of course, this is going to give us, this is 400, so it will give us 200 times 10 times 10 to the negative 6, plus this will be 144, which will give us 72 times 20 times 10 to the negative 6. If you compute this, our total energy using your calculator should be able to give you, this is 2000, and this will give us 144, and so we have 10 to the negative 6 into 2000 plus 1440. And when we compute that, finally, it should be able to give you final energy as 3,440 times 10 to the negative 6, which, if you want to standardize, will give you 1, 2, 3, will give you 3.44 times 10 to the negative 3 joules. So the total energy will approximately be 3.44 times 10 to the negative 3. You can quickly capture that, and that answers part A. Now part B is asking that if the capacitors are now joined positive to positive and negative to negative, find the final common potential difference. Now whenever we say positive to positive and negative to negative, understand that these capacitors are now in parallel. Or whenever they tell you that a capacitor, another capacitor is connected across, then you know that those two capacitors they are mentioning or talking about are in parallel. Now, for part B, since they want us to find the common PD, it automatically means that we need to actually find the charge, even in the first case. Because we saw last time that for us to find the common PD, the charge, the total charge of these two capacitors in this first state here is supposed to be equal to the charge that will flow when the capacitors are joined in parallel. So for part B, the capacitors are now joined. If I can draw the sketch that joins these two capacitors, they are now joined with the positive of one to the other. It is still the same capacitors, 10 and 20. And they want us to find the PD, if I simply sketch my diagram like that. They want us to find the PD that is developed there. Of course, we know that for parallel arrangement, we use addition. So if we let C be the effective capacitance here, then our C is simply going to be 10 plus 20 microfarad, which is, of course, 30. This means that from charge is equal to CV, the charge here will actually be 30 times 10 to the negative 6 times V. The charge that will flow in this arrangement will be that. But this charge must be equivalent to the total charge here. If we look at diagrams A and B, diagrams A and B, we shall have from Q is equal to CV, since we have C and V, the total charge will be equivalent to 20 times 10 to the negative 6 times 10 plus, for the second case, 20, 10. 10 as this is for the first case. 20 is the PD times 10 times that, plus, now 20 is the capacitance times 10 to the negative 6 times 12. So the total charge here, if we compute, will give us 200 plus 240. So it will give us 440 times 10 to the negative 6. This will be coulombs, and I can call this 2. The charge before, total charge in case A of the question should be equal to the charge in case B, in part B. In other words, the 440 times 10 to the negative 6 should be equal to the 30 times 10 to the negative 6 times V. And this V is the PD we are looking for. So, of course, this will cancel, and our PD, which is V, will be 440 out of 30, which will be definitely 44 out of 3, which will be 44 out of 3. And when you compute that, it should be able to give you approximately 14.67 volts. 14.67 volts. It should be able to give you that. So the condition we use is that the charge flowing in the arrangement at the start, the separate arrangement, the total charge should be equal to the charge that will flow even when the capacitors are joined with similar plates joined together. Now they want us to find the energy stored by the combination. They want us to find the energy stored by the combination. That is the energy stored in the second case when the capacitors are in parallel, as B part 2. And we'll expect that this part of my chalkboard is already captured. You are focusing on that part, and give you a few minutes to capture that solution so that we can together move to the next part. To find the energy stored by the combination, that is B part 2, we looked at the energy at the initial arrangement, and we saw that energy is given by a half CV squared. Do not get tired of stating that expression for the energy and take an assumption that the examiner already knows that I know that expression. In physics, the formula is very key, and it earns you marks. In events where the symbols have not been talked about, you are expected to explain the symbol meanings. So the energy here will be given by a half times the effective capacitance is 30 microfarads times the PD that we have just got, which I can take as 44 out of 3 times 44 out of 3 by squaring. If we compute this, of course, it will give you a final answer that I will state here. When you compute, it should be able to give you 3.227 approximately times 10 to the negative 3 of a joule. That should be the energy. And they are asking us that where has some of the energy gone, which we call the loss in energy. Energy loss is supposed to be energy at the start minus energy at the end. Remember, we said that when these capacitors are connected together directly, the one that has more charge will lose charge to the other until when they get a common PD, which we have just looked for. So that implies that the energy they have finally is expected to be less than the energy they had at the start. And the loss in energy in this case, much as they are not asking for it, they are asking us to comment about it, so we should be able to get its value, which will be got by looking at that difference. And getting the magnitude, this is rounded off to around this figure. But ideally, the comment they want, which we even saw last time, is to show that the difference in energy here is lost as heat in the connecting wires of the circuit. This energy is lost as heat in the connecting wires of the circuit. It is lost as heat in the connecting wires of the circuit. Last but not least, they are saying, suppose the above capacitors were instead joined positive to negative. What would the final PD be? Suppose they were joined positive to negative, what would the final PD be? If they were joined with positive to negative, that means they are joined in series. It means they are joined in series, and our sketch would actually now look like so this is 10 and 20. Now, if you remember in our expression where we were deriving the effective expression for the capacitors, there are two methods. One quick method would be using Q is equal to CV, but we can get the effective capacitance here, which would be product over sum, and this would give us 10 times 20 times 10 to the negative 6 times 10 to the negative 6 over the sum, which is 30 times 10 to the negative 6. So our effective will actually have 20, because 1 0 will go over 3 times 10 to the negative 6 farads. This is capacitance. Now, this is the effective capacitance. But as you are aware, the PD we are looking for, V is equal to the individual PDs there. We are looking for V, and V is V1 plus V2. And since it is a one-wire circuit, it means that the charge flowing is the same. And therefore, since we saw that Q is equal to CV, it implies that V is equal to Q over C. So since we already know the total charge, as 440. 440. I'll get V1. The PD I'm looking for is actually going to be equal to Q out of C1 plus Q out of C2. That is one way. That I'll get my V as the total charge, which was 440 micro, out of, okay, times 10 to the negative 6, out of my C1, which can be 10, plus 440 times 10 to the negative 6 for micro, out of 20 times 10 to the negative 6. Of course, that will cancel. That 10 to the negative 6 will cancel. 1 0 will cancel, and I'll get 44 plus this 0 will cancel, and I'll get 22. So you find that the PD will be obtained as that. But alternatively, from Q is equal to CV, we can still get our V as Q over C. We can get our V as the total charge over the effective capacitance, this one. If you choose to use this, you'll get the total charge as the PD will be the total charge, which is 440 times 10 to the negative 6 divided by 20 times 10 to the negative 6 over 3. And this 10 to the negative 6 will go away. This 0 will go away. So you stay with ideally 22. This will give us 22. 22 divided by 1 out of 3, which is 22 times 3, which is still 66 volts. So there are several approaches that candidates are expected to use. In science, there are several ways of killing a number. There are several ways of killing a number or solving a number in that matter. And whichever way is used, these questions cannot condition you that using this approach. However, there are questions where you may be conditioned, and when you are conditioned, usually we expect that your solution should abide by the condition. If you don't abide by the condition, you'll get the correct answer, but it is like if they tell you you must go to such and such a place, but you must pass through particular points. If you don't, and they were awarding tickets to verify you've passed there, you'll be caught off guard. That number is accomplished, and we can now proceed to look at yet another number. We can proceed to look at yet another number. I have emphasized that this is one of the most common phrases they will always give you. This is one of the most common phrases they will always give you. My dear producer, I told you particular numbers, and this is not one of them. We can move to some other number. My producer, not that one. Not that one. Yes, that one. My dear students there, you already have these numbers, remember? That is if you took the snaps or the peaks last time. So just identify that you have it and we get rolling. Identify that you have it and we get rolling. This number here is unique in a sense that it uses the dielectric. At the start, we talked about the dielectric constant. We defined it. We talked about dielectric field strength. I will simply remind you of questions that you should be able to define. You are expected to know how to define dielectric strength. The ability of the material used as a dielectric to withstand a breakdown of the system or the capacitor. is the dielectric strength. The maximum potential gradient that the dielectric material can withstand before breaking down is that. So you should know how to define that. You should know how to define dielectric material, or otherwise looked at as relative permittivity. You should also know the uses of the dielectric in a capacitor. So now that this question has the dielectric constant, we saw that capacitance is given by that expression. We saw that capacitance is given by that expression, where the dielectric constant here is what we are calling the permittivity of free space. Now, if we look at the question at hand, we have a capacitor with a capacitance 100 microfarads. But they are saying if a material of dielectric constant 3 is slid in to occupy half of the overlapping area of the capacitor, what does the capacitance become? If it is slid in to occupy half, it implies that if it is slid in to occupy half, then we can look at these scenarios. At the very start, if this is my capacitor, it has air as a dielectric. If we slide in the dielectric to occupy half, then we can look at if this is half. The capacitance here is C. Now, if it is half, and we put it this way, it means this will be a half C, and this is supposed to be a half C. But there is a dielectric material here whose permittivity is 3. And they are asking us what does the capacitance become if they put in that occupy half. Now, before I slide it in, I can also look at this capacitor. If I slide it in here, this is now different from that. If I look at this capacitor before sliding in and separate it into 2 and connect them together, I will have a half C and a half C, as I've told you. This would be a half C, and this would be a half C. But when I put the constant there, because these capacitors are now in parallel, if they are connected like this, they are in parallel, that means this will be 50, and that will be 50. Now, if I separate them like this and I put in this will have the material times the value of the capacitance there. If this was 100 and this is a half of 100, it would mean this is 50, and therefore this will become what? What we are going to get, you can even quickly tell that this will become 3 times. So, if I call them this way, I say after separating them, I have this. This is C1, say this is C2. If I put in my dielectric, this C2 will be 50 microfarads, and C1 will actually be 3 times 50, which will give us 150 microfarad. It will give us that. In other words, we can say that the effective capacitance in part 1 that they want, if I call it C1, would be a half of C times the dielectric constant, which would be a half times 3 times 100. And this will give us 150 microfarads. So the total capacitance, therefore, because they are in parallel arrangement, will be 150 plus 50, and this will give us 200 microfarad. You recall one thing, that E is equal to E naught ER. So ER will be equal to E over E naught. That is what I mentioned here, what we call relative permittivity. Relative permittivity is defined as the ratio of the capacitance of the arrangement or the capacitor with the dielectric in between to the capacitance when the space between the plates is a vacuum. And when the plates are vacuum, it means that our expression will be E over E naught. Now, as we move to the next case is if the dielectric were to occupy fully half, then this is the capacitor. If it occupies half, we would have our interpretation drawn like this. And if we are to connect and call this C1 and this C2, it means that we now have capacitors in series. And they're asking us to find the capacitance of the combination. We have already quoted that capacitance is given by that. And now this will be a half D, and this is a half D. So C1, which has a dielectric, will actually be 3 EA over a half D, and C2 will be just EA over a half D. That implies that if we are using the series arrangement, we definitely must find the effective by using product over sum. Since there are two capacitors, we can use product over sum to find the effective capacitance. So using our 1 over C equal to 1 over C1 plus 1 over C2, our 1 over C which we want C will be equal to 1 over, that will be 3EA over D over 2 plus 1 over EA over D over 2. If we rearrange this, as you are aware, this will be 1 over C will be equal to. This is, for those who may see it disturbing, it is like 1 over B over A over C. So it is 1 over B divided by A over C, and it definitely becomes 1 over B times C over A. So it is C over BA. So you need to see what our B is and what our A over C is. So I want to move it to the next step here and write it as 2. 2 is the C. And A and B are multiplied now. That this will go up, and we shall have C C over BA. So if our B is that times that, it will be 3EA times D plus, again, 2 over EAD. If we solve this, remember we already have these values. We have our C, our EA over D as 100. So if we substitute in, we want C, our LCM becomes what? EAD. This 2 is common, so we have 3EAD, 2 plus. This will give us 3, 6, 1 over C, and our C will become 3EA. I hope I've not interchanged this. This D will go up. 1 over C will become D over 6 EA plus D over 2 EA. So it implies that if we take the LCM, that will simplify to 6 EA will give us D plus, this will give us 3. 1 over C becomes that, and this gives us 4. So C becomes 6 EA over 4 D, which is the same as 3 over 2 times EA over D. EA over D is the capacitance. So we say that, but our EA over D is 100 microfarads. So it means the capacitance that we are looking for will be 3 over 2 times 100. And this, of course, is microfarad. And this will give us 150 microfarads. If the arrangement is changed, the effective capacitance should be able to be that. As we capture that, I'll request my producer to give us our last question. Our last question, number 22. Number 22. Number 22. Number 22 is in a different exercise, not that one. The one in a separate file according to the work that I showed you. There is a number that is in a separate file, not from that slide. The number in a separate file, my producer, is the one I want. Yes, if you can find a way of magnifying it for the students to see. Yeah, dear students, that number where we have multiple capacitors is the one I want to wind up with, and we have no time. So I will simply interpret it such that if time gets us before we finish, I'm not going to sketch so much, but it could be important for me to sketch in order to emphasize what I want. I see our time is not on our side. So I'll use the technique of interpreting it, well aware that you already have enough knowledge to do such a number. I will simply interpret it and expect you to be able to finish it, because the time will not allow us to finish it. Now, we have 2 microfarad here. We have 8 and 8 here. I want to start from there. When you move from the source, the only way you can tell that a given capacitor is in series or parallel with the other is when you meet a junction. Like now, when you reach here, there is a junction. Charge will continue going this side, some charge will come this side. Now, this charge that goes this side reach here, there is another junction. And charge will continue going this side, some charge will go this side. But when you meet these 2 capacitors, you see here, 8 and 8. 8 and 8. I will start from there. They are in series because they are connected by 1 wire. Therefore, if I call their effective C1, we shall use series, we use product over sum. We shall get 64 out of 16, which will give us 4 microfarad. Now, when we get the 4 microfarad here, that 4 that we have got will be again in parallel with this one, because it will take this space. So I will say 4 microfarad and now 2 microfarad. They are in parallel now, so we simply add. And I'll call this C2 will be 4 plus 2. And this will give us 6 microfarad. Now, that 6 microfarad is now occupying any space along this wire. I will come this side and look at this 6 and this 6. They are in a parallel arrangement. I will add them. So I'll have 6 and 6. I hope you are following. And they are in parallel, so we shall simply add them. I'll call that C3, 6 plus 6. And my C3 will be equal to 12 microfarad. Remember here, I have this 6. Now I have 12. That 12 will be in series with this 3. The 12 that I have got will be in series with that 3. And now if I look at 12 and 3 in series, again we use product over sum. I'll call that C4. 12 times 3 out of 15. And of course, this will give me 12 out of 5 microfarad. Now, that 12 out of 5 is here alone now. Now, if we move from here to there, this and this, we look at the arrangement. This side we have 6. Now we have the 12 out of 5. We have this and that. Since when charge reaches here, it will go. It means these 2 are again in parallel. So 12 out of 5 and then 5. We look at those 2 and they are in parallel, so we simply add them. And when we add them, what do we get? We'll have C5 as 12 out of 5 plus 5. And this will give us 25, 37 out of 5 microfarad. Now, finally, if we have to sketch, we have this. Let me show you, and this, and another capacitor here, and we have that connection. We have this. This is 6. This is 4. This is our 12 out of 5. And this is our 5. So if I work on these 2, before I do this, if I work on these 2 are in series. These two, 4 and 6, 6 times 4 out of 10 will give us 24 out of 10 microfarad. I'll call that C5. Now my C5 is 12 out of 5. And this is in parallel with this one. It is now in parallel with that one. And we again get the effective, which will be C6. And then we shall consider the effective here with that one. If you finalize in the interest of time, your final capacitance should be able to give you a figure of 24, a figure of 2.44 when you finalize, 2.4489 microfarads, and they want you to get energy which you can get by substituting there. In the interest of time, I don't want to enter so much into the next program. I want to thank you for attending the lessons faithfully and want to encourage you to continue practicing, continue reading. Remember, if you want to be the best, you must work more than the rest. I want to thank you and wish you a nice weekend. Stay at home, continue reading. God bless you. Gachai.
Somera mu ddiiro lyo ng'ewagiddwa Maryland High School erisangibwa Entebbe. Ssomero ly'abawala n'abalenzi lusomesa arts and sciences okuviira ddala ku siniya esooka okutuukira ddala ku siniya ey'omukaaga nga lisangibwa mu kifo ekiweeweevu obulungi. Tulina ebisuula eby'omulembe, science laboratory ssaako ne computer lab wamu ne.
She gives you her number, but your pen didn't work and the bus is gone. Get a pen you can rely on. Big Crystal, the long-lasting pen with perfect ink flow.
Wamune.
Green Hill Academy has high standards of learning and the teachers are very good. They give you a sense of belonging.
Green Hill has helped me to discover my talent.
The environment is good.
Encouraged us children to be excellent.
Wamune.
Combo University, a private chartered university that offers world-class education at all levels, including certificates, diplomas, bachelor's and master's degrees. Our courses include computing and IT, law, journalism, nursing, business administration, education, fashion and design, and many more. Admissions for the August 2020 intake are still open. Will you join us?
Wamune.
Kids Kingdom Kindergarten and Daycare. Somero ly'abaana bato. Omuzadde leeta omwana ogenda okola ebibyo. Ebyokuzanyisa by'abaana byonna mu nsi tubirina. Ate nga abaana we bazannyira wagazi nnyo. Jjukira security enka. Amasomero gonna gali mu kikomera. Abasomesa be tulina bakugu mu baana. Abaana tubaliisa bulungi nnyo munnange. Tulina main campus e Buddo Naggalabi nga bwakayisa Buddo Junior.
Fellow Ugandans, thank you for being patient and mindful of others during this very